So first off, the agenda. Kind of wanted to talk about what the genesis behind the report, why we did this study, the methodology we used, some of our findings, and quick summary, QA at the end. So the reason behind the study that we performed, we wanted to understand how enterprises, or what factors enterprises use to make decisions about which cloud providers to go with. And what we found is generally they look at these four things, like the global presence. They want to understand how many data centers a cloud provider has, where they're located, how many data centers are in their availability zones. Pricing obviously is a factor that can drive decisions. What services the providers offer. So is there a technical fit? What do the architectures look like to deploy load balancer or firewall infrastructure for your services? And then last is performance. And what we found was that, and from a performance perspective, how do they differ? How do they compare against each other? And are there any gotchas? And what we found was that there's a lot of information around the first three topics, but not so much around the performance, specifically the network performance side. When we did a search, we found that there was really no sort of comprehensive view of performance, network connectivity performance against these three providers. There was no information that gave us a sense of trend. Maybe there were some views around snapshots, and certainly no information or no comprehensive information comparing the network architectures of the three providers. So we decided to do our own study. And so what we did is primarily using active-based monitoring approach, where essentially you can think of us sending out pings and trace routes, though enhanced somewhat. We were replicating either users or replicating connectivity between their different regions availability zones to understand what the network connectivity and the characteristics of the network look like. So first, we ended up deploying what we call agents, monitoring agents, in Google Cloud, AWS, and Azure, and their different data centers in different regions. And then we also ended up deploying agents in tier 2, tier 3 carrier facilities, basically out on the internet, so we could replicate end users from different parts of the world, connecting back to the different regions of these providers. Essentially, these agents would periodically trigger a test, which meant we would replicate a user interacting or trying to connect to another agent at the Google Cloud or at the cloud provider side. And the test would typically consisted of TCP-based probes. We did essentially use something like traceroute, except we used TCP-based traceroute as opposed to ICMP. The idea is we wanted to kind of avoid some of the issues that occur with ICMP with rate limiting, or we wanted to make sure our metrics were reflected more of what the end user experience would be, which a lot of those applications tend to be TCP-based. We also ended up running these tests bidirectionally, so from remote agents in the tier 2, tier 3 colo facilities to Google and Azure, AWS, and then vice versa. And the idea was we wanted to understand if there was asymmetry in the routing and what impact that had on the performance also. So in addition to basically gathering network telemetry and gathering information such as loss, latency, jitter, and the active network path in both forward and reverse paths, we also appended additional, I would say, contextual data. So things like AS information on the transit hop, so we kind of get a sense of what different carriers some of our traffic would be traversing. We looked at added a GeoIP information to get a sense of what part of the world some of this traffic was getting routed through, and then also looked at things like link delay and whatnot. So all this information ended up getting fed to a cloud-based central reporting and correlation engine. And the idea is that, first off, we had continuous access to these agents, so if there were any issues, we were able to resolve them. Luckily, there were no problems. These tests ran periodically every 10 minutes for 30 days, and the idea was to get a sense of trend, not just do like a spot test. We ran it for 30 days. We thought that if there were any outages, also potentially some of the noise would get filtered out in some of the averages. Luckily, there were no significant outages during this time frame, so we think the data wasn't significantly polluted. And as I mentioned, all this data was then sent over to a cloud-based correlation and reporting engine. Most of the study does involve us looking at the network connectivity architectures and some of the differences in the latency between the carriers, between the providers. We didn't really see too much difference in the loss and jitter information that we collected. Now, as far as the sort of the use scenarios that we were focusing on, kind of get classified into these 4 categories. So one was the end user measurements. So I mentioned that we had our agents in a couple of tier 2, tier 3 colo facilities. The idea is that we would be monitoring from some points on the internet to the different cloud provider regions. Then we also looked at interavailability zone connectivity. So for Google Cloud, Azure, and AWS, we picked a few regions where they had availability zones to validate, to understand what connectivity and latency looks like within a region. We looked at inter-region measurements. So for instance, you're in Ashburn in AWS trying to connect to London or Oregon, Ohio. We wanted to understand what those characteristics look like and what the network connectivity looked like there. So connectivity within the backbone. And then the multi-cloud use case. What does connectivity look like between all 3 cloud providers? So obviously a lot of enterprises are leveraging some combination of those to host different services. So this becomes a relevant use case. For the end user measurements piece, we basically, as I mentioned, had, I think we monitored from 27 remote locations, from different tier 2, tier 3 colo facilities to 15 regions in AWS, 25 regions in Azure, and 15 regions in Google Cloud. So we'll just build this up real quick. So the idea was to get a full, sense of a full mesh and understand what latencies look like from different regions across the world, different parts of the world to the different regions in all 3 cloud providers. Just this combination alone resulted in almost 1,500 tests, being run, executed. All right. All right, and then for the interavailability zone measurements, we selected a few regions where this capability existed, and we had agents deployed between data centers within each availability zone. I think we looked at 4 regions for AWS, 4 regions for Google Cloud. We only looked at 1 region for Microsoft Azure, just because at the time we did this study, which was last summer, they were only starting to deploy this type of concept, and so there was only 1 region where we had this capability to test. As for the inter-region measurements, again, that was a full mesh of tests between all of the between all the regions within each cloud provider. So we talked about 15 for AWS, 25 for Google Cloud, 25 for Azure, and 15 for Google Cloud. We'll move past this a little bit. And then as for the last use case, which was the full mesh use case, again, for the multi-cloud use case, again, we did a full mesh of tests where we basically measured connectivity between each of the regions and each of the cloud providers to a region and the other cloud provider. So there's basically a full mesh between 15 to 25 to 15. So you basically get a significant number of tests, combinations of regions that we're testing here between the different providers. But all of it over the course of running this every 10 minutes for 30 days resulted in 20 million unique data points. And we ran these tests bidirectionally, so now we get doubles to 40. And then from each of these sort of test data sets, we pulled out loss information, latency, jitter, and the network path information. So essentially, something like 160 million data points that were used in the analysis. So now that we have the data, what did we learn? What were we able to extract? So the good, the bad, and the ugly, so to speak. So for the first case, the interavailability zone, a lot of the cloud providers claim LAN-like latency, within a region, which makes sense because that's the whole point of availability zones is for HA or to support applications with low latency requirements. And what we generally found was indeed they met that claim, right? So you can see at AWS we tested within US East 1, AP South 1, EU West, and different providers. But the point is that within each region, we basically saw about 1 millisecond or sub 1 millisecond latency. So that's good. So it makes sense. They have resilient and backbones. The data centers are relatively close to each other, so we see LAN-like latency. Now, for the inter-region testing, we saw some interesting, I would say, results here. So inter-region really means that so within each provider, AWS, Google Cloud, Azure, we ran tests between every region. So again, Virginia, Ashburn, let's say, communicating with London, communicating with Ohio, communicating with something on the West Coast. And we basically ran these tests, and so the point is we ran these tests and we had some latency metrics. The first thing we were able to uncover was that all the inter-region traffic traverses their backbone. So there's no internet component involved, there's no third-party carrier, everything stays within the three providers network, right? So, which makes sense. But the point is we had these latency numbers for inter-region connectivity, but we had no reference point to say, is this good, is this bad? So what we ended up doing was taking our monitoring agents, which were also deployed on the internet, the tier 2, tier 3 carriers, and running tests between combinations of tests between agents that were in the same region. And the idea was to get an internet reference baseline, right? So just to get a data point to understand is the traffic, the latency within these provider backbones better than the internet, worse, comparable, just to get something to compare to. And what we generally found was that the latency within these backbones were generally comparable to the latency we saw on the internet between the same regions. In most cases, it was actually a little bit faster. And actually, what these bar graphs represent for all three providers are the sort of number of inter-region pairs and what category they fall into. Are they faster than the internet, same as the internet? And for the most part, they were. But what's interesting is that there were a handful of outliers. So if we look towards the right, there are a few, there are some inter-region pairs that fall into the 30% slower than the internet category. So if we focus on one of these, first off, what we see is primarily this seems to be within the Asia region. So for instance, what we're looking at right now is latencies through these cloud providers from Sydney communicating to Tokyo, Singapore, and Mumbai, India. And you can see that Sydney talking to Tokyo through their backbones is a little bit faster than the internet, or roughly comparable, I would say, in terms of the internet latency. But if we look at Singapore and Mumbai, they're about 30% higher, slower than what the latencies we saw on the internet. Azure obviously did not meet that. Azure seems to be comparable to our internet baseline, but the AWS and GCP, it seemed like they were a little bit slower for this specific combination of inter-region pairs. Now, if we look at the end user use case, so in this particular instance, what we're looking at is, let's say on the left graph, we're talking about some of our agents deployed at tier 2, tier 3 colo facilities, again, replicating a user, interacting with the data center in Virginia for all three providers, AWS, Azure, Google Cloud. And what we see is, as we group these users into different regions, whether they're in Asia, Europe, North America, so on and so forth, the latencies tend to be somewhat comparable, right? They don't look all that different between the three providers. And we generally find that seems to be more or less the trend in the North America as well as Western Europe. So on the left, we show you an example of the data for Virginia region, and then on the right, we show you an example of the data for London or for UK. But if we look at Asia, this is where we start to, or some regions in Asia, this is where we start to uncover some differences. So in this case, we're looking at the latencies from our end users, and again, the end users are grouped into where they are located by geography. So users in Asia, our agents in Asia, our agents in Europe, our agents in North America. In this particular instance, communicating with the 3 cloud providers in Mumbai region, right, or in India. And the first thing that stands out is that the latency for the users in Europe is 3 times higher for Google Cloud, for GCP, as compared to AWS and Azure. Right, so the question is why. It's pretty significant delta. And if we look at the if we start to dive into a little bit of the path data, the detailed network telemetry, what we see is that they are taking a suboptimal path. So what we have here is an aggregated view of some of our pathing information. And on the left, we see some of the agents that we're monitoring from. You see some of them are in England. There's one in Germany, I think one in Spain. You can also see that the Google network, which is sort of represented by the green coloring on the right. First up, you see that the agents ingress into the Google backbone fairly locally, fairly quickly. But the point is that it seems that in this case, the traffic is getting routed through the US and then ultimately on to Mumbai in India. So obviously, it's taking a very long path. And the question becomes why, right? Why is this traffic into this region taking such a suboptimal path? And what we see is if we look at the fiber connectivity map for Google's backbone, what we noticed was that there was no direct link from Europe to Asia, to Mumbai. So actually, you ended up getting bounced through the Middle East, back to Western Europe, through the United States, and on to Asia. So it kind of made sense why we were seeing such a big discrepancy. Right, so that was the first thing we noted. The other thing we found some interesting observation point was that if you see how these user regions are clustered, you see these black lines, which really represent the variance. I would say the variability in the latency numbers that we measured. And what we see is that AWS, the yellow bar, AWS particularly in Asia, shows a lot of variability in the numbers. Certainly, so a lot more than what we see with Azure and Google Cloud. So the question becomes, why are we seeing these kinds of things? And first off, the question is this an anomaly, or is this something we see across the board? And if we dive into or look at this information for several different regions, not just Mumbai, but Tokyo and Singapore, we do kind of see that there is more variability for those other regions in Asia. But Mumbai seems to, by far, be the worst in terms of the variance in the data. And if we look at, again, looking at our pathing information, our path data, what we ultimately discover is that the AWS likes the internet. So basically, if we look at, let's say, as an example, one of our agents or a user in Frankfurt trying to talk to the 3 cloud providers to their regions in Singapore, what we ultimately see is that most of the network path is over the internet for AWS. We actually see that we don't even hit the edge of the AWS network until Hong Kong, and then ultimately we get routed to Singapore. Whereas for Azure and Google Cloud, we actually ingress their backbones relatively close to where that end user is located. And obviously, the internet being a best effort network, numerous providers involved, you're probably not going to get as good a performance as you would through these controlled backbone environments. As a matter of fact, we're able to show this in our pathing data. So again, if we look at for AWS as an example, if we look at our agent, where there's one in Milan in Europe and there's one in Singapore, and what we see is that these sort of nodes in the center really represent different AS or different carriers that our traffic is traversing, and you can see that we don't even hit the in this case, I think we're talking to the Ashburn region, Ashburn data center, but we don't even ingress the AWS network until, in some cases, Ashburn itself or in Dallas in the US. So again, most of the path is over the internet, which results in a lot of variability in the metrics. Whereas for Azure and Google Cloud, we see the opposite really, where we ingress those backbones relatively close to the end user. What's interesting is that we came out with this report in October timeframe. So the data was collected around July timeframe. We came out with the performance report in October, and I think at the reInvent conference in November, AWS announced another service called the Global Accelerator, which is like a premium service essentially, where they, instead of using their sort of hot potato routing methodology, they will offer kind of do something similar to what Google and Azure do, where they will onboard you onto their backbone relatively quickly. So what we're seeing basically is a monetization of their backbone. And we know this is obviously more of a trend. This is not isolated to AWS. We know that Google Cloud also offers a tiered sort of premium versus standard offering, where the standard, again, is kind of more akin to the AWS hot potato routing scenario, as opposed to so you use more of the internet. We haven't seen that with Azure yet, though. Now, on the multi-cloud side, where we tested connectivity and the performance between all three cloud providers, all different combinations of regions, we actually noted that they all peer directly with each other. So connectivity is pretty good. You're not going to traverse a third-party carrier. There's no internet component involved. They must have clearly have a symbiotic relationship, and they peer directly with each other. We didn't really see any issues with regards to jitter or loss. So latencies, what we would expect generally. But one thing that was interesting was that even within the context of this multi-cloud peering directly with the peering between AWS, Azure, and Google, AWS still used sort of the hot potato routing approach. They wanted to get off their backbone as quickly as possible, and get on the Azure and Google Cloud backbones as quickly as possible. So, what can we take away, from from the study itself? So not all clouds are obviously created equal, right? We definitely saw differences in terms of how some of the network connectivity is architected. We also, for instance, we saw less performance stability in Asia, just because AWS prefers the internet before you start traversing their backbone. Geographic performance varies, right? So geography does make a difference. There's more variability, or it could be slower performance in different parts of the world. Again, Google Cloud was 3 times slower from Europe to India. Intra-cloud performance is pretty good, right? So the backbones are pretty robust. Connectivity is good. So the inter-availability zone performance was in the sub 2 millisecond range, which is what we would expect. And the last thing is, I would say multi-cloud is a safe bet, right? So a lot of organizations have services or adopting services, migrating services to different cloud providers, and the connectivity is there to make that a safe bet. And sort of, what is the goal of the study? What are the recommendations? The idea is we want to enable you to have data, use data when you're making decisions. It might be a good idea to also understand what is the best and worst region pair relative to where your data center is located in terms of when you're making decisions. Obviously, you want to understand the network connectivity architectures of the different cloud providers. So for instance, in AWS, you might end up traversing more of the internet. So you just be aware of that if that's going to be an issue for the service that you're providing. And then, obviously, inter-region performance can also be an issue, right? So as we noted in the Google Cloud case, you might have a component in EMEA. There might be something dependent on something in Asia, and the performance may not be there. So again, you want to have data to validate that where you are hosting your services is not going to be a problem. And in the end, trust but verify. So this was a first iteration of the study that we undertook, and there's no steady state in the cloud, and so we're going to be doing this again this year, and we'll be curious to see if there were any changes made, if we still see that high latency in Google Cloud from Europe and Mumbai, or if that's changed. But other things we're also considering adding is expanding the study to include other cloud providers, We're looking to also, most of the study so far has been around IPv4, so we're also looking to compare IPv6 versus IPv4 performance and connectivity. And then also, taking into account other connectivity types, private connectivity, express route, direct connect, which so far has obviously was not included yet. So this was a summary, but obviously there's a URL where you can download. There's actually a full report where you can get more detailed information about some of the data that we presented, on this URL. Thank you.